The overall goal of this procedure is to create an aperture optical trapping setup to trap particles of about 20 nanometers in size. To do this, a detector is added to an existing optical laser trapping setup to enable measurement. Then, the nanoparticle solution to be measured is dispensed into a microfluidic chamber with the double nanohole trap, and the chamber is loaded onto the optical trapping setup. When a particle enters the illuminated aperture, light transmission increases dramatically because of dielectric loading. If the particle attempts to leave the aperture, decreased transmission causes a change in momentum outwards from the hole, and by Newton's third law, results in a force pulling the particle back into the hole, trapping the particle. The particle causes a redshifting of the transmission curve, which can be monitored. Hence, the trap can become a sensor. Ultimately, results can be obtained that show trapping events of nanoparticles, including unfolding of trapped proteins, as indicated by changes in the laser intensity through the double nanohole.
The main advantage of this technique over existing methods like gradient force optical trapping is that it can trap smaller nanoparticles with lower laser intensities.
This method can help answer key questions in biochemistry, such as how do single proteins fold and interact, and how do virus particles infect living cells.
Generally, individuals new to this method will struggle because it's difficult to integrate the double nanohole into an existing laser trapping system.
The optical trapping setup is based on a Thorlabs optical tweezer kit equipped with a force measurement module. An avalanche photodiode is used to replace the quadrant detector in the force measurement module. When setting up the optical trapping system, eye protection should be worn whenever the laser is on. Make sure the beam will be contained within a safe area by operating in a closed room and confining the beam within the trapping setup as much as possible. Reflective jewelry should be avoided. Latex gloves are worn to ensure cleanliness of the optics. Set up the optical tweezer kit and the force measurement module according to the manufacturer's instructions. The assembled optical tweezer kit has an inverted light microscope design and is composed of the following: a trap laser, a 100x oil immersion objective, a 3-axis sample positioning stage, and a CCD camera. Please note that electrostatic discharge protection is advisable when handling laser diodes. The force measurement module allows for calibration of the optical tweezers using positional detection of the condenser's back focal plane. A silicon-based avalanche photodiode, or APD, is used instead of the force measurement module's quadrant position detector. Also insert a resistor capacitor, or RC filter, using a 200 kiloohm resistor and 100 picofarad capacitor. This is used to reduce the high-frequency noise and facilitate seeing trapping events on the oscilloscope. Use a coaxial cable to connect the RC filter after the APD. Then, use coaxial cables and a T-adapter to connect the oscilloscope and data acquisition module to the RC filter. The system is now ready for sample loading. The double nanohole aperture is made up of 2 nanoholes milled into a gold film by a focused ion beam. The film is 100 nanometers thick and supported by a glass substrate. The nanoholes overlap to produce 2 sharp cusps. Nanoparticles will be trapped in the gap between these cusps by laser light that is incident on the double nanohole. Large registration features should also be milled in the metal film to help identify the double nanohole location in the optical microscope setup. These features should be about 100 microns away from the double nanohole. Pour 10 grams of polydimethylsiloxane, or PDMS base, and 1 gram of curing agent into a disposable cup. Mix for a few minutes. Then, evacuate the mixture in a vacuum chamber until all of the bubbles are gone. Next, pour 1.5 grams of PDMS into a 9 cm diameter Petri dish. Spin coat the PDMS onto the bottom of the Petri dish at 950 RPM for 65 seconds. Following the spin, the thickness is not critical as long as it is under 80 microns. Gently place 3 to 5 number 1.5 cover slips onto the PDMS such that they do not overlap, and evacuate for 30 minutes. If, during the evacuation, the cover slips moved and are stacked one on top of each other, gently move them off each other. Be sure to keep the PDMS under cover slips thin and uniform. Then, evacuate Petri dish again for 30 minutes. Remove the Petri dish from vacuum chamber and heat it on hot plate for 20 minutes at 85 degrees Celsius to cure the PDMS. Once the PDMS is solidified, use a razor blade to cut along the edges of one of the cover slips. Then, using fine-tipped tweezers or a blade, gently pry up the slide. A thin layer of PDMS will adhere to the cover slip. Place the cover glass with PDMS in a new Petri dish. Then, using a razor blade, cut out a 3 mm by 3 mm window in the PDMS. This window will form the chamber where the nanoparticle solution will be kept. Use a laser cutter to fabricate an acrylic microscope slide holder with a 3/4 inch diameter hole at the center. Tape the circumference of the hole with double-sided tape. Use a razor blade to cut away any excess tape. Place the fabricated microscope slide on one of the prepared PDMS-coated cover slips so that the PDMS is sandwiched between the glass and acrylic. Using a micropipette, add a few drops of 0.05% weight per volume polystyrene nanosphere solution to the PDMS window. Add a drop onto the gold film where the nanoholes are located. Place the gold sample on top of cover slips with the nanoholes inside the PDMS window. Make sure bubbles are not present in the chamber. Then, press the gold sample against the cover slip and dab any excess solution. Since an oil immersion objective will be used, add a drop of oil on the other side of the cover slip, on top of the PDMS window. Take note of the location of the nanoholes. Insert the microscope slide into the slide holder, oil facing down. And then, lower the slide holder until the immersion oil makes contact with the microscope objective. Roughly align the slide stage such that the registration marks milled in the gold film are underneath the objective. Using image acquisition software such as Thorlabs, which is included as part of the trapping kit, find the registration marks on the gold film and follow the indicator lines up to the nanoholes. Position the slide such that indicator marks and other open areas are cleared from the screen center. Excessive light transmission can damage the APD. Turn on the laser. Since the dichroic mirror is not perfect, a spot near the center of the screen from the laser beam should appear. Using the piezo stage control software, further refine the alignment on all 3 axes. When the alignment is correct, the maximum APD voltage will be observed, indicating the highest transmission through the nano aperture. Now that the system is set up and the sample is loaded, optical trapping data can be acquired. With the help of the indicator marks, position the spot close to a known nanohole location. The double nanoholes will be too small to be resolved clearly and will appear as small dots on the screen. The light transmission through the sample is indicated by the signal level on the oscilloscope. Further align the sample as to maximize light transmission. Be careful of indicator marks and visible and non-visible scratches, as light transmission will be high in these areas. Nanoholes will show sudden jumps in light transmission, while scratches exhibit more gradual changes. Using the wave plate, adjust the light polarization to achieve the highest light transmission, as the double nanohole structure is polarized. To acquire data, sample the APD's voltage using the data acquisition module for the desired time. Acquisition times are typically in the hundreds of seconds. In this case, custom software is used for data acquisition, and the voltage is sampled at 2000 times per second. Using MATLAB, filter the acquired data using a Savitzky-Golay filter and plot it versus time on a graph. To show trapping of 20 nanometer polystyrene nanoparticles, the transmission through the double nanohole was measured as a function of time using the APD. Optical transmission was then plotted over time. The trapping event is characteristically sudden, with a sharp edge, showing a clear switch between two transmission power levels. As shown in this example, there is frequently an increase in signal noise in the trapped state. This noise increase comes from the Brownian motion of the trapped particle. Note that without the trapped particle, this noise source is not present. Some artifacts may show up in the results that are not indicative of trapping events. Results showing drifting, seen as slow changes in the transmission over a period of minutes, as shown here, should be discarded.
Following this procedure, other methods like Raman and fluorescence spectroscopy can be performed in order to answer additional questions about the nature of the nanoparticle that is trapped.
After its development, this technique has paved the way for researchers to study biologically relevant nanoparticles at the single molecule level. For example, to sense protein binding and to study virus infection both at the single molecule level.
After watching this video, you should have a good understanding of how to integrate a double nanohole optical trap into an inverted microscope laser tweezer system to trap single nanoparticles.